Now in addition, as I said, there is a program counter or instruction pointer. This is also a 64-bit register. And there are some segment registers. Well, here I'm not discussing in detail about segment registers. You can read into any textbook or any PDF on Intel x86. You will understand what these segment registers mean. Basically, every memory address that is generated that is combined with one of the segment registers to generate the actual physical address. Okay. And there is a 64-bit condition flag register which contains various information about the operations which was carried out just in the immediate past. There are flags like 0, sign, carry, parity, interrupt enable, and so on. Many are there. And there are some control and debug registers as well. These also you do not need right now. Okay. Talking about main memory address, here it's interesting. We just mentioned, just go back to the previous slide, that the instruction pointer was 64 bits, which means your memory address that you can store in this IP is a 64-bit memory address. Now in this Intel processors, all these 64 bits are actually not used. So we talk about a 48-bit virtual or logical address, which is the address generated by the CPU. But just like your IP register, there are other registers also where you can store a memory address. They are all 64 bits in size. But out of them, the most significant 17 bits will be either all zeros or all ones. You cannot have any other combination. So you are having remaining 47 bits plus those 17 bits either 0 or 1. So effectively 48 bits of information you can have. So that is your 48-bit virtual or logical address. Now depending on what kind of processor you are using, this logical address gets translated into physical main memory address, which can be 36 to 40 bits in size. Okay, fine. Now these are a few things you need to remember, because otherwise you will not be able to understand how this assembly language code that the compiler is generating is working. Now you see there are 16 general purpose registers I had said. You see RAX and RDX, they can be used to store the return value from a function. Which means when you're calling a function, the function is returning some integer, suppose. So that integer return value will be loaded in the RAX register before the function returns. Similarly, when you are calling a function, the first argument as a matter of convention will be stored in RDI, second argument will be stored in RSI, third in RDX, fourth in RCX, fifth in R8, sixth in R9. If the number of arguments are more, then there is an indirect way of passing the arguments. Okay. And the registers which are marked as callee saved, these means that if inside the function you are using these registers, then it will be your responsibility to save and restore the values of these registers before you return. Because the calling function will assume that you are not making any changes to these registers. So these have to be saved if required by the callee function and restored before it returns back. Okay. And as I said, RSP is a stack pointer, because in x86 there is a stack which is maintained in memory. There are instructions like push and pop, just like in stack, where stack pointer always points to the top of the stack. And as a matter of convention, the stack grows from higher memory address to lower memory address. Suppose initially this stack pointer contains the value 100, and if I want to push a 32-bit number, so the stack pointer will get decremented by 4. It will now become 96, and the 32-bit of data will be stored in the higher 4 memory location bytes. Okay, so stack grows towards lower memory addresses that way. Okay. Now, when you compile a C program, there are various flags you can use. Now this capital W all means that W all means that means all compiler warning messages will be displayed. So it is just a good practice to include this whenever you are compiling something, so that if the compiler is generating any warning, you can also see those warning messages, right? And this capital S flag minus capital S with a C program, C file as parameter, will be generating the assembly language equivalent. It will not generate the executable code. It will generate a file main.s, which is also a text file. It contains the assembly language equivalent of that main.c C program. Okay. Similarly, if you have another program fact.c, another file, you can also use -s to generate fact.s. Now from assembly, if you want to generate this object code separately, you can use the -c option. -c option will be generating object code. Similarly for fact, it will generate the object code. And if you run GCC with all the object codes, then you will be getting the final executable. Okay. Now in the first assignment that you'll be doing in the lab, you will be having to analyze the assembly language code that is generated by the compiler. So you will have to use this -S option. Okay. Fine. Now there are some conventions which are followed in the x86 assembly language. This you have to remember. Like there are many instructions using which you can move some data from one register to another. You will see that most of the instructions will be move from here to here, there to here. Those are the predominant kind of operation, register to register transfer or register to memory, memory to register, like that. But when you do this kind of transfer, you can specify whether you are transferring a byte, a word, long word, or quad word. So you'll be prefixing that move instruction like move B, move W, move L, or move Q. It will tell the assembler, or means you can know by seeing that whether you are referring to moving 1 byte, 2 bytes, 4 bytes, or 8 bytes. Right? And regarding the registers, there are some register naming convention as well. Like I mentioned that there are 16 64-bit registers. Let's say RAX was one of the registers. Now you see this box on the left. This RAX, if you mention %RAX, it means you are referring to the contents of the register RAX. That is a 64-bit register. But if you write EAX, it means the lower 32 bits of this register. That means you are in 32-bit mode, you are possibly doing arithmetic only on 32 bits. Then you will be writing EAX, that means lower 32 bits. Similarly, if you are writing AX, %AX, which means lowest order 16 bits. Now in the 8086 kind of processors I mentioned, it was a 16-bit processor. That time this register was called AX. And AX was divided up into two halves, AH and AL, high order, low order. %AH means the high order 8 bits of this AX. %AL means low order 8 bits of this AX. Okay. Now the same kind of naming convention you can use for the other registers also. Like here on the right, I have taken an example for this R8 register. Okay. Well, if you write just percentage R8, it will mean the whole R8 register, 64-bit. But if you write percentage R8D, D refers to double word. It means the low order 32 bits. If you write R8W, lowest 16 bits. If you write R8H and R8L, this means the lowest means 8 bits, the high order and low order. Okay. So like this, you can refer to different segments of your register, either the whole register, low order 32 bits, low order 16 bits, and so on, whatever you need. Okay. So this is what I've just now mentioned, that according to this convention, AH or AL will refer to an 8-bit register, 8-bit number. AX will refer to a 16-bit register. EAX will be 32-bit and RAX will be 64-bit, right? Now, depending on whether you are using a 32-bit or 64-bit instruction, these register names will be generated as E or R. EAX means 32-bit, RAX means 64-bit. Just a second. Just a second. Sorry. Yeah. There was an interrupt request I had to service. Fine. Now, there is something called addressing modes, which you will be studying in detail in your computer organization class. Addressing mode means when you are accessing some data, there are various ways you can specify where your data is located. Because your data can be stored in a register, it can be stored in a memory location, and if it is in a memory location, there are various ways you can specify the memory address. Okay. So here, some of the most commonly used addressing modes are shown with the help of examples. Well, let me see. First one is global symbol. The instruction is like this: move Q. Move Q, as I said, means move quad word, 64-bit move. X is a global label. X is the address of some instruction. So you move that instruction into register RAX. Okay. Contents of that memory location. So memory location whose address is X, that will be moved to RAX. Now immediate is an addressing mode where you specify the value directly as part of the instruction. And immediate numbers are denoted by this dollar symbol. Like if I write move Q $56, percentage RX, then this number 56 will be moved into the RX register. Okay. There can be a register to register move. I can say move Q RBX RAX, which means this RBX, whatever is there, that will be copied to RAX. There is an indirect addressing, memory indirect it is called. So example is like this: move Q. Now within bracket, I am specifying a register. This means whatever is contained in RSP, that is treated as a memory address, and whatever is stored in that memory address, you take the data from there. Okay. So RSP will contain some memory address, and the contents of that memory location, mem RSP, I'm writing like this, that will be copied to RAX. There is a base relative kind of an addressing mode, which is a little more flexible, where in addition to that indirect, you can add an offset. Like here I've used -8. move Q -8 within brackets some register number. This means the data stored in memory location RBP -8, that will be copied to RX. And lastly, this addressing mode is a little complex. This is used mainly for accessing array elements, one-dimensional array elements. Here, again, we have an offset like -16, and there are three things you specify separated by commas in bracket. Let's say RBX, R6, two registers and a number 8. This means RBX -16 you add as usual, and RCX and 8 is a scale factor. You multiply them together, then add. And whatever is the address, you access memory from there. Now recall, whenever you store a one-dimensional array in memory, if each array element occupies 4 bytes, then your scale factor will be 4. To go from one element to the other, you'll have to increase the address by 4. So that way, this 8 here, 8 means it was scale factor is 8. Like that, you can compute the address of individual array elements and access them from memory. Okay, fine. Now let us come to the interesting part. For understanding the assembly code that will be generated by a compiler, you need to refresh your memory. You had studied it earlier regarding function call and return. What happens? Well, these are some slides I've taken from your first year programming and data structure course. I believe some of you may find these slides familiar. So I'm just very quickly going through this. Suppose there is a main function and there is a function called GCD. The main is calling GCD with two parameters A and B. These are the formal parameters. These are the actual parameters. And inside this function, GCD, this X and Y are the formal parameters. Now you recall, it was mentioned that whenever there is a function call, there is something called an activation record which gets pushed in the stack. And what are the things the activation record contains? See, whenever you make a call GCD, it will first contain the return address. After completing the GCD, where in the main function, the control has to come back. That return address has to be stored in stack. Then return value, well, return value may be as part of activation record, may not be, but in general, it can be here also. So when the function returns a value, it can be here as part of the activation record, and all local variables that you declare, these parameters X and Y, and in addition, all variables you declare inside, which are not static, of course, they will all be allocated space here in the stack. So every time you make calls to a function, this activation record will get pushed in the stack. So if there are nested or recursive calls, the stack will go on growing. These activation records will be pushed one on top of the other. Okay, that way stack will grow. So this is another example where you see main is calling NCR and NCR is calling fact 3 times. Okay, so when NCR will be calling fact, so the activation record corresponding to this call will be stored in the stack. And NCR will be calling fact 3 times. When it will be calling fact for the first time, so activation record for this fact will be pushed in the stack. Fact will complete, then it will come back. So this will again be taken off. You will be getting something like this. And this will repeat 3 times because there are 3 calls to fact. It will be pushed, popped, pushed, popped, pushed, popped. And finally, when this NCR returns back, you have nothing. All these activation records have been cleared from the stack. So you have whatever was there originally. Okay, fine. Now let us come to some real assembly language code and see that how they look like. Okay. Here I have taken a very simple function, a function that computes the sum of two integers x and y and returns the value. So if you compile this using the M32 option with IA32 assembly, the code that would be generated will be something like this. Now please note that this code may vary from one version of Linux to another. So there can be small variations from one machine to another, but roughly it will be something like this. Let us see. Let us try to understand this code. Now EBP is the base pointer. Now, all addresses that are generated that are with respect to a base pointer. Now, whenever the main function was executing, the main will be calling sum, right? Some other function will be calling this sum. So there was some value of the base pointer. Now, when you have called sum, you should not disturb that base pointer. That is why I am pushing the value of that base pointer in the stack, right? Since I have given push L, L means long, that means 32 bits. This is a 32-bit code that is generated, so it will be push L. But if it was a 64-bit code, it would have been push Q. Q means quad. Then SP is the stack pointer. Recall, we are more concerned about the stack because all these parameters will be stored in stack and we have to access them from there. So whatever is the present value of ESP, we are not disturbing that. We are copying it to EBP. Move long ESP to EBP. Then we are using this kind of index addressing mode 12 EBP plus 12, this memory location, whatever is there, you move it to EAX. So what is there in plus 12? Because the stack pointer always points to the top of the stack. See here, return address was there, then the two parameter values x and y was there, and just now we have pushed this EBP. And now it is pointing here. Now, if you want to access x, you'll have to have plus 4, plus 4, plus 4, plus 12. So if you do a plus 12, you are actually accessing the number x. Number x you are storing in EAX register. Then you are saying add. What you are adding? 8 EBP. 8 means plus 4 plus 4 y. You are adding y to EAX. EAX already contained x, right? So now the sum of x and y is stored in EAX register. Now you recall when we showed you the registers, all the 16 registers we mentioned, that EAX or RAX register is by convention used to store the return value from a function. Now we have already stored the return value in EAX. So we simply pop the value of EBP. We had pushed it in the beginning, restore EBP, and you return to the calling function. This is how this code works. Now, are there any questions? I can just make a pause here, and if there are any queries, we can take.
There is some question from Shubham Mishra.
Shubham Mishra, let me see.
What if I want to use higher 32-bit of RAX? I think it was a while ago. On the chat. Could you see, Ayushi? Hello?
Hello. Yes, fine now. what if I want to use the higher order of 32 bits of RX, right? You
Mhm.
see, directly you cannot access the high order 32 bit, but there are indirect ways. You can do a 32 bit write shift. You can shift the data to the right by 32, and then you can access as the low order EX, right? That's how you can access it indirectly, not directly. Well, see, this, as I said, that this different segment registers which are there, usually we access memory locations with respect to the segment registers. Just a second. So this EBP is also a segment register. Now I want to use this EBP register index with some number to access the various elements of the stack. Well, I don't want to use the stack pointer SP directly because I don't want to disturb the stack pointer because it should be kept at the same value as it was earlier. Okay. So what I do, I temporarily copy the value of stack pointer to the BP register, base pointer, EBP, and use that EBP register to index and access the values of X, Y, and so on. Okay. Well, every instruction does not cost one cycle. Depending on the complexity of the instruction, number of cycles can go up. Well, even for the simplest of instructions, number of cycles are more than one. But you have something called a pipeline mode of execution, using which effectively you complete one instruction execution in every cycle. That is the ideal objective. But in practice, the number of cycles per instructions will be greater than one. Well, that CFI I'll come later. CFI. Well, EBP means, well, EBP is a register. So EBP will contain some value, and mem of EBP means whatever is there in EBP, that is a memory, that is treated as a memory address, and mem of EBP means content of that memory location. Okay. Well, here we are pushing EBP in the stack because the function from where this function add was called, maybe it was already using EBP. Now inside this add, if I modify the value of EBP, then that value would get lost. So it is a good practice. So whatever registers you do not want to modify, at the beginning you push it in the stack, before returning you pop it back. So the value is restored. Okay. Well, EBP, EAX, functionally they are not different. As a matter of convention, as I said, they are used in different. For example, push and pop instructions, they by default they modify SP. Stack pointer gets modified. But for the other kind of index instruction, you can use any instruction. You can use BP, you can use AX, BX, anything. And well, move minus 20 RBP EDX. This means you add minus 20 to the value of the register RBP. RBP contains some address in memory, some point in the stack. You add minus 20 to it. And whatever is the value, load the value from that memory location. That is the idea. And store it in EDX. Yes, ESP is the original stack of main. You're right. If you see, just a second. See code. see the code once. So in the assembly language instruction, you are saying that we have written only return. So how are you returning a value? Okay. Now you see in the slide where we had shown you the register conventions. There we had mentioned that the AX register by default is used to return value from a function. So because already our value of t, the result, is stored in EAX, we already have it there. So we do not have to do anything else. The program which had called add will take the return value from EAX. Move $56 RAX will directly transfer 56 into RX register, right? That is immediate addressing. Directly it will transfer 56 into that register. See, when we write EBP equal to ESP, we are not changing base pointer to stack pointer. Rather, whatever the stack pointer contained, it is some address in memory, right? That address is copied into EBP. Because you see the activation records are stored in the stack, and we are copying the value of stack pointer into EBP, and you are indexing it to access the various elements of the activation record, X, Y, and so on. Well, mem EBP plus 4 will not refer to any valid data because your stack has grown only up to EBP. Oh, EBP plus 4. Plus 4 means the immediate value down below it. So you're pushing values one after the other, right? Let me see the slide once. Yeah. Plus 4 will be the EBP value that you have already pushed in the stack. Yes. Now in the code that I have shown you, this EBP plus 4 will indicate the value of the old value of EBP that was pushed in the stack as part of the first instruction. See, these instructions are not always dependent. These instructions are dependent on the processor, the hardware chip, the CPU chip which you are using inside your computer. These are specific to that. Okay. Percentage EBP is used in assembly language usually to indicate that it is the contents of the register. Percentage EBP is used. Yeah. You should use percentage in assembly language instruction. Well, there was one question that in the chart it is said that RDI stores the first argument. Then why are we again storing it in the stack? Because you see, it may be storing the first argument, but the way we handle nested calls and recursion, these activation records must be maintained. So even if RDI, RSI, the values are coming from there, we will first have to put them in the activation record. Then we have to do the rest. Okay. I'll show some examples later. Well, stack can be anywhere in memory. So wherever you have a free space in memory, you can initialize your stack pointer with the highest address in that portion. So from there, your stack will grow towards lower address. Stack can be anywhere in memory. Return access EAX. EAX is the first return value by default. EDX, normally EDX is not used. EAX is the default return value. EDX is sometimes also used. Well, you're saying why EBP plus 4 not used instead of EBP plus 8 for the address of X. Just one thing you see, EBP plus 4. See, EBP plus 4 will be what? EBP is pointing to the next free element in the stack. So every time you do a push, after pushing an element, the stack pointer gets decremented by 4. So if you say EBP plus 4, it will point to that stack element where the old value of EBP was stored. If you write EBP plus 8, then it will point to Y. EBP plus 12, it will point to X. So you're extracting the values based on the index values. Yes, stack will already be initialized by the calling function. Whenever you are running main a.out, someone initializes the stack and then calls main. The OS initializes the stack and then calls main. Main is also a function which is called. Okay. Mem EBP plus 4 are not same, because EBP plus 4 means you're adding 4 with EBP. Then that is your memory address. See, here I am trying to give you a flavor of how assembly language looks like. I am not trying to teach you assembly language. You will have to dig deeper and know all these details. I'll just give you a cursory feel of how this assembly language looks like, what are the meanings. Then as part of the first assignment, you will really have to dig deeper and try to understand and explain how an assembly language that is generated is actually working. Well, so Abhijit, I will answer your question after I get back to the slide. Okay. Look, all local variables are declared in the stack as part of the activation record. Well, so PPT, now the questions are based on that diagram. I need to go back to the slide to explain that.
The slide is there. Are you not being able to see?
No.
You are not seeing the slide, right?
No, I'm not seeing the slide.
Sir, but we are seeing the slides.
I'm seeing the slide.
Yeah, now I think it is coming. Yeah, now I am seeing. Yeah.
Okay.
Okay. So there are several questions based on this diagram. Let me just explain this once more. Here, a small snapshot of the stack is shown. This is one activation record. This activation record shows you that return address, then the local variables, the parameters, X and Y. In fact, I think I missed one more. There will be another variable called T. T will also be there. I missed that. Sorry. So these corrections you can make. I may make some small mistakes. So T will also be there. Okay. So these +8 and +12 are used to refer to the relative value. This EBP will be here. This will be T. So you can make that changes. So when you're adding 8, each element is 4 bytes long. So +4 you come here, +8 you come here to Y. If you make it 12 +12, then +4 +4 +4 you come to X. So each of these elements are 4 bytes long. So if you are doing +12, you are skipping 3 elements. If you are doing +8, you are skipping 2 elements, like that. Okay. Fine. I think you can go to the next slide. You can continue. Okay. There are a couple of other instructions called leave and enter. Well, if you look at the code generated by GCC, GCC does not use leave. It does not use enter. but it uses leave. Now, you see, the activation record that we are talking about, that is sometimes also called a stack frame. So the stack frames are pushed one after the other every time a function is called. Now the enter instruction basically sets up a stack frame of the required size. Depending on the number of parameters, number of local variables, the size of the stack frame can be adjusted. Now, because the size of the stack frame is not fixed, so usually GCC, instead of using the enter instruction, it uses 3 explicit assembly language instructions like this. So here I'm using the 64-bit version, push q, move q, sub q. It saves base pointer. It moves stack pointer to base pointer as usual. Then it subtracts n from the stack pointer. It means it subtracts n from the stack pointer so that space is created in between to store n bytes of data. So whatever is the size of the stack frame, that you can specify in this n. And the leave instruction is typically used just before the return instruction from a function. It does just the opposite. It copies RBP back into RSP, and then it will pop this RBP from the stack. Okay. So you will see this when you look at some of the codes generated. And there is something called assembler directives that you need to know, that you will see when you generate the assembly code that there are many lines which start with a dot. See, whatever starts with a dot is not a machine instruction. It is not an executable instruction. Rather, those are some instructions to the assembler. Some examples are dot file, dot text, dot global, dot type, dot word, dot byte, dot string, etc. Similarly, one of you asked something like dot CFI. Under dot CFI, there are many such assembler directives. Now these CFI assembler directives, CFI stands for current frame index. These are normally not required for normal machines. Normal machine means the kind of machines that we use. But for some target machines, when you want to do exception handling and debugging, then you may require this additional information. But if you look at the assembly code that is generated from some sample code, you will see that a lot of the CFI statements will be generated in between. That may be disturbing your, you can say, understanding of the code. Too many such lines will be coming in between. So I have just given a way at the end that how you can prevent these from appearing. If you call GCC with this flag, then the .cfi lines will not appear in the .s file. Okay. So in your assignment, when you will be doing it, the first assignment, you can use this. Okay. Let me take some illustrative example, but again, don't expect me to explain each and every line. It is your final task to understand this and do assignment 1. I'll just tell you some of the important things so that you understand how overall the things are. Okay. This is a simple C program containing only the main function and the corresponding assembly code generated. If I use the -S directive by GCC, it's shown. So the blue window shows the assembly code. So let us look at the main function first. There are 3 local variables A, B, C. A and B are initialized to 20 and 50. C equal to A plus B, then print sum is C, return 0. So if you look at the assembly language code, you see in the beginning, there will be some introductory section where the name of the file will be here, that it is a text section. By convention, text means program code. Dot section means name of the section. Each section is given a name. Then this printf, you have defined a character string, right? Sum is %d. So here that string is defined. Okay, and there is a few other directives, so ignore that for the time being. But the actual machine code is here on the right. You see, the first 3 instructions, they correspond to that so-called enter I talked about. Push Q, you save the value of the current base pointer. You move the current stack pointer into base pointer, and you subtract 16 from stack pointer. Why 16? Because, well, here integer by default, each value will be taking 32 bits. So so this A, B, and C are the 3 local variables which are defined, and there will be the return address. So a total of 16. So this 16 will be subtracted from this RSP. That creates the stack frame. Then you see you have written A equal to 20, B equal to 50. That has been done in the next 2 statements. The value of 20 is getting stored into this RBP value -12. -12 means A. 4, 4, 4. A is the bottom, then B, then C. Similarly, 50 -8. -8 means B. So they are stored. That means A equal to 20, B equal to 50 is done. Now there's a statement C equal to A plus B. You again have to retrieve the values of A and B. So you get the value of A, you store it in EDX, a register, get the value of B, store it in EAX, you add EDX to AX, so result will be in EAX only. Okay. Now EAX by default is a register through which you return the values, but here there is nothing to return. Here you are trying to print. Now see, this red marked instructions are those corresponding to the printf. You see, after A plus B, you have to store it in C. So C is where? C is -4, RBP means C. First A, then B, then C. -12 is A, -8 is B, -4 is C. So this EAX gets stored in C. Here, before calling printf, you have to set up some index values like this $.lc0 means this string. This string pointer will go to EDI. The value of the number will go to ESI. Then you call printf. 0 means EX means it's 0 is a parameter for printf. Then you call printf. And finally, after printing is over, because you're returning 0, you are moving 0 to EX. EX contains the return value. Then you give leave and return. This is how this program works. Okay. So this you can understand. If you have any confusion, don't ask me now. You sit with it, try to understand, try to do a Google search, and you try to understand the code, whatever you will be asked to do. Okay. Those will be fairly simple programs. So let's move on with some more examples. Just look at this, just a function. Sum int x int y, int t equal to x plus y, return t. See here, you again push BP, store RSP to BP. This will be doing for every function. These two things are mandatory. Then you will be, you see, this EDI and ESI, if you look at the convention, EDI and ESI will contain the first and second arguments to a function. So the first argument I am storing in -4 RBP, first element below, and ESI I am storing in -8 RBP, 2 elements below. Then I have to execute this t equal to x plus y. I have to retrieve x plus y, x and y. So I retrieve x, get it to ESI, retrieve y, get it to, add to ESI. So the result will be in ESI. You store it in T. So T will be in -12. You see, this machine code or assembly code is generated by turning the optimization flag off. If you turn the optimization flag on, some of the instructions will get eliminated. Okay. So here you are seeing the code without optimization so that you can make a one-to-one correspondence and understand it easily. Okay. And finally, you will be returning T. So the value of T, you are moving to EAX, which is supposed to contain the return value. Then you are popping RBP return. Okay. This is how it works. So let's look at just another function where you have a main function which is calling another function called factorial. Fact. N equal to 7, val. There are two variables defined here. And inside this fact, A is a parameter and prod and I. There are three variables defined here. Okay. Let us see how the machine codes look like. For the main, so here I'm showing the machine code for main, that part. Push Q, move Q, subtract 16. So again, it makes space for the stack frame. Then before calling fact10, it makes some adjustments here. It will have to pass the value of n. So the first the value 7 will be stored in n. So here 7, it is -8 RBP means n. And that n, it is stored in EAX before calling fact10. It goes to EDI, then you are calling fact. And after fact, the return value is supposed to be in EAX. So that EAX is stored in val. -4 RBP means val. -8 RBP means n. -4 RBP means val. Then you have to do a printf. Again, there are some statements for this printf. You have to retrieve the values of n and val. So -4 and -8, n and val you are returning. Then you are calling printf. And finally, again, return 0. Move 0, leave, return. Okay. So these are similar. If you look at it, you'll understand. Same way. Let us look at the function fact. Fact again, you see here, you are pushing RBP, moving RSP to RBP. Then you are this logic. There is a for loop. Inside the for loop, you are multiplying product with I, storing it in prod. This loop will go on. So you see the instruction. I'm not trying to explain the logic. I will explain what these instructions mean. You figure out the logic. See, move, you know, move means you are storing 1 to this. You are storing 1 to this. -8 and -4 refer to this I and prod. Both are initialized to 1. Prod is 1. I is also initialized to 1. So you are moving 1 to this, also 1 to this. Then you jump to L4, come from here. Now here you are moving Now you're comparing whether a loop is over or not. You move this to EX, you compare this with this. You compare I with A. First one is I, you compare with it A. Compare means it does a subtraction, trial subtraction. After trial, you check jump if less than or equal to. If it is less than or equal to, it should continue. So if it is less than or equal to, you go to L5, it will continue. If it is not, it will come out of the loop. Okay. So as long as it is less than or equal to, it will continue to L5 and it will continue to do this multiplication. You see, multiplication, then addition, prod equal to prod into I, it will do this. And at the end, when it is coming out of the loop, it is supposed to return prod. So it is already, prod is already in EAX. So it is already there in EAX. So you simply pop and return, right? So in this way, you can interpret these code which is generated. Let's take another example which is a little more complex in the sense that you have a main function which is calling a function NCR. NCR in turn is calling fact. So there are three functions: main, NCR, and fact. So in a similar way, you can interpret it. I am not trying to explain each and everything to you. So I have given you the main pointers how to start understanding what are the meaning of the different things. Just let me show you. This is the main. For the main function, this is the assembly code as shown on the right. So these are the headers, this string, etc. And this push, move, subtract 16, all these things are there. There are three variables, 3 into 4, 12, and return address 16. So it is 16. And 7, n equal to 7, 7 goes to minus 12 RBP. Minus 12 RBP is n. 3 goes to minus 8 RBP. Minus 8 RBP is R. Okay. Then result equal to NCR NR. So you load the first parameter in EDX, second parameter in EX, move them to ESI, EDI, call NCR. Well, here you could have reduced the number of instructions, but as I said, the compiler is not an optimizing mode, so it is not trying to optimize. Call NCR, and after NCR, the result return value is in EX. You store it in result. Result is minus 4 RB. Then printf. Printf, you know how to call printf. That's similar way. After adjust this, there are in our result. There are three parameters. Store them in these three registers. String, call printf. Then return 0. Okay, same way. So you look at NCR. Well, NCR is again similar, but factorial is called 3 times. You see, once it is called here, once it is called here, once it is called here. And there are some divisions, integer division. There's some division here also, IDIV. So you can interpret the logic. So it is calling fact 3 times. Now each time it is calling, the return value is available in EX. So it is storing it somewhere in ECX. Here again in EX, it is storing in ECX, ESI, and so on. Now you may see here that there are some peculiar instructions like CLTD. So what is CLTD doing? CLTD is used for sign extension. So whatever result, you see, whenever you are doing a divide instruction, you see, addition and subtraction are fine. For addition, you add two 32-bit numbers, the result is 32-bit. You add two 64-bit numbers, the result is 64-bit. But when you divide, the convention is you divide a 64-bit number by a 32-bit number. The result is a 32-bit number. So your first operand, you must make it 64-bit. So this CLTD is a sign extension command which makes a 32-bit number as 64-bit. So the previous instruction stored the result in EAX. The CLTD will make EAX into RAX by sign extending a 64-bit. Then divide is called. Similarly here, before divide is called, again you are calling CLTD by making it sign extension and then call. Okay. And factorial is very similar. You already saw a similar code earlier. So again, I'm not going into the logic. You figure out the logic. So the instructions I've already said, CMPL means compare. You compare 0 with something. You see, if A equal to 0, this minus 20 means A. You are comparing 0 with this. If it is jump if not equal, you go to 6. Otherwise, return 1. Move 1 to AX, jump L7, return. L6 means you are coming here, prod equal to 1. 1 you are storing in prod, I equal to 1. 1 you are storing in I, jump L8. Like this, you can find out the logic, right? So this will be an exercise for you to understand the logic of these statements. This is a bubble sort. I'm skipping this because you can work it out. So I'm not going into the detail of this code. This is a rather long code. But I would like to show you the last function of this bubble sort program, which is a swap function that uses call by reference. Now this call by reference, you recall what you do here. Here, instead of passing the values, you are passing the addresses, right? A pointer to XP, a pointer to YP. So whatever is coming as parameters, they are addresses and not actual values. So let us look at the code. You can relate what is actually happening. Well, first two instructions are as usual: push RBP, move RSP to RBP. Then, well, first two parameters by default they are passed through RDI and RSI. So RDI you store in XP, RSI you store in YP. -8 is XP, -16 is YP, right? Then the next statement is temp equal to star XP. Temp equal to star XP. So what we do? First we retrieve the value of XP. What is XP? -8 RBP. This is an address, right? This is not value, this is an address, a pointer. So this pointer is moved to RSI. That is a pointer, not a value. Just remember this. So using indirect addressing within bracket RSI means memory location pointed to by RSI that is moved to EAX, which means star XP. The value gets stored in EAX. And that you will have to store in temp. That is stored in -20 RBP means temp. Similarly, next line is star XP equal to star YP. So -16 RBP is your YP, the address of YP that you bring again in RSI. Now again indirect addressing content of RSI, memory location. So the value of YP goes to EAX and you will also have to find out the value, the address of XP. So address of XP also I am bringing to RSI. Then this EAX I am storing in memory location pointed to by RSI. So here this star XP equal to star YP is happening. Similarly, in the next three statements, the last statement is happening. So like this, you can actually understand and correlate how these pointer things are going on, right? And one last example I'll show you. just a recursive function, a trivial recursive function for factorial. This is a factorial function, and this is the corresponding assembly code. Well, this is also fairly easy to understand if you look at it. First, you see push move as usual. So you're subtracting 16, then move EDI minus 4, then compare 0 with n. You see, this EDI will contain the first parameter n, so that you are storing in minus 4 in the activation record, and you are comparing with 0, comparing 0 with that. If it is equal, you return 1, move 1 to EX and return, jump L3. Otherwise, you go to L2. L2 is this recursive call. So here you bring again the value of n, subtract 1, okay, and that you move it to EDI, that is your first parameter for a function, call fact. This is a recursive call. EDI will contain, see, means here EDI contain the first parameter. So here again, you store it in EDI and make a recursive call. And after it comes out, you multiply the value of n with whatever is returned by the function. That is how recursion works, right? So the code for recursive function is fairly simple here in case. You see here, I do not want to discuss anything more here. So PPT, can you see the assignment so that I can just show them the assignment once?
Yes, I will. I'll pull up the assignment.
Yes, yes.
Just wait for a while.
So your first assignment is basically based on whatever I have briefly tried to discuss. You will be digging deeper into the code. Don't expect that I have understood each and every line. I may be wrong somewhere. So you can correct me wherever I am wrong.
Assignment 1. So I will. This is Word file, so I'll do a application share.
No, whatever.
The Word file is opening. Wait.
So,
Can you see? No.
Not yet.
What is wrong? Open application window. Just I'll do it once more. I don't know what's going on. Anything other than PowerPoint, sharing becomes a little bit of an issue. So I'm here. Now it should work. Can you see?
Not yet. Yes. Not yes.
Right?
Yes, yes.
Yes, sir.
Fine.
Should I make it smaller?
No, I think it's okay. You can slowly scroll it up so that everyone can see.
Okay.
See
okay,
here.
So if you keep talking, I'll just.
In this assignment, basically, you will be understanding two assembly language programs. we have furnished the corresponding C code, C programs. You will be generating the corresponding assembly codes. You will be understanding it. And how do you know you have understood it? You will have to comment each and every line of the code. You will have to annotate the assembly language code in a very nice way so that we understand that you have understood it properly. So the two programs are as follows. First one is a very simple program. You see, this is your first program. Just there are two numbers, you have to find out the greater of the two and print it. Simple. This is your first program. The second program. Go to the next page, PPT. Yeah, this one. So this is again a toy program. Here you're basically calling a function GCD4, which computes the GCD of 4 numbers. Okay. And GCD4 in turn is calling another function GCD, which computes GCD of 2 numbers, like this. So the code is self-explanatory, nothing to explain. But you will have to understand the assembly language code. That is the objective. So the statement of the problem, can you see in the beginning, PPT?
Yes, it is here.
Yeah. Yes. These are the things you have to do. Translate the following two C programs using GCC Linux to the assembly language of x86, 64-bit you compile without optimization. Do not use optimization. So rename the generated assembly files as with your roll numbers like this, where roll is your roll number. Then add comments for each line of the assembly language program. Your comment should explain the functionality of the instruction and connection to the original C program. Also make sure that your commented file can be compiled to generate the executable file. And this is an individual submission assignment. So then all of you have to submit it individually. So PPT, you can add anything if you want to.
No, this is absolutely fine. This is assigned date is today, and the submission date will be 9th.
Next Wednesday midnight.
And you will be submitting to Moodle.
Yes. Just understanding x86 assembly language is very important because ultimately your compiler that you will be designing will be generating this kind of a code. Okay. So understanding this is very important.
Okay, so let us go and check if there are any questions on this.
Yes. Yes.
So I'll stop the sharing right now. Let's see.
Just Ishan, you can ignore the assembler directives for the time being. Those who did not annotate. Okay. Just only the executable instructions. Move, call, add, subtract, divide, like that. The slides will be shared on Moodle. The slides you can get. Yes, slides.
Actually, I mean, can't they see the slides on Team also? The slides are already on the Team.
Means on this Team also slides are there. And just please check whether these slides you can see or not. Pankaj, can you see the slides? Pankaj, Abhijit, we have uploaded the slides also here on Team also.
Yes, sir.
You can see that, right?
Okay.
So I will just have one general question on Moodle. I mean, have all of you been able to get into Moodle, or you still have any issues? Because we will now start operating on Moodle for the assignments. Have all of you been able to get in?
Is there anyone who is not logged into Moodle yet? Registered under Moodle yet?
Yeah, please. I mean, you have raised hand, so please go ahead. Vamsi or any.
Hello, sir.
Yeah.
So I registered through my old email ID, which I had previously in the first year. Is it fine?
Those things you sort out with the Moodle Central, right? If you have any ID issues and so on, because
No, I was able to log in and
yes, if you are able
enroll.
to log in and see the courses, then it's fine. That's it.
Okay.
Just get yourself enrolled in the course. That's it.
Yes,
We have
sir.
given you the student key, right?
Yes, sir.
Beyond that, we really do not need to know anything. Yes, Piyush?
Now the Moodle server is handled centrally.
Piyush is saying something.
Piyush, please.
I don't think the compiler lab version.
No, your voice is breaking, Piyush.
There's an internet issue.
Piyush, it would be good you write on the chat. Your voice is breaking. Please write on the chat. Shudhanshu, you can go ahead and. Oh, Piyush, you couldn't find the enrollment key.
Enrollment key was there in the slides.
Have we, Srijani, did we share the slides?
The slides are there in the Teams only, sir. The first introductory slides.
May not be there in the Teams. The key was generated afterwards.
No, the key was there in the slides. You had showed during the slides.
Oh, really?
Yeah, because everyone has enrolled after that. I've checked. There are around almost 100 people have enrolled. So I can just share the key. I mean.
Oh, this is. I shared, but it got messed up in the format. Let me share it in right format.
Is the institute module, right? Shudhanshu is asking the CSE module or institute module?
Institute module.
Not CSE.
No, not the CSE module, the Moodle Central. Here are the keys. Yeah, now we should be able to see.
Yeah. These are the keys for the theory and the lab courses.
Right.
I think that was a typo, must be a typo. That should be .s.
.s only, right, Srihash. You are absolutely right. There's a typo.
There's a typo.
Your generated assembly file should be .s. We'll correct that. Sure. Okay, so since you are being able to connect to Moodle, so we will put up the assignment on Moodle immediately. Showman, would you please take care of that? You are doing that, right?
Yes, sir.
Right, so please correct this typo, and we have the final form of the assignment. Please put it up on the Moodle and send out an announcement.
Okay, sir.
Thank you, Sean.
So, Rashil, the reason we are not using CSE module is mainly related to a management issue. Now we are not having the regular lab people taking care of the Moodle server. That's why it's much better to have the central infrastructure and use it. That's why maybe. The slides are on Teams. We shall also upload them on Moodle.
That's right. Any other question?
As you can understand, x86 assembly language is not very trivial. There are a lot of complicated things there, particularly relating to the assembler directives. There are a lot of quite complex things.
Yeah, but it's not. I mean, it just needs a systematic study. It's not
Yes,
that difficult.
systematic studies required.
That's it. Okay. I don't think there's any other question immediately.
Yes.
So over to you.
So I shall have to figure out why I'm not able to share.
Yeah, that you figure out separately. We'll have a